Okay, while we wait for the projector to warm up, let's get started. So how many people are still doing P3B? Why do the people who always do things late never come to discussion? Okay, so not sure why this is going on. All right, actually, let me get some help. Hey, okay. All set up. Excellent. Thank you. Okay. Great. Anyway, hopefully you can all still hear me. So if people don't, I was actually planning to answer some questions about P3B if people had any, and then move on to P4A. But if not, okay. All right. P4A, in my opinion, is sort of the easiest project that you will have this entire semester. Okay, so you guys already know all about concurrency and locks and acquires and pthreads. So this should just be like a simple exercise for you. Okay. So how many people here know how HTTP server works? Okay, cool. So can you tell us?
How it works?
Yes.
Well, it opens the TCP connection
Okay.
on port 80 on a web server,
Okay.
and it waits for clients to connect to port 80 over TCP,
Mm-hmm.
and then you have to give it an HTTP command, usually a get or a post request,
Mm-hmm.
and then ask what file or resource you're looking for.
All right.
And it sends it back to you.
Cool. So as Mark explained, a HTTP server is your browser is basically a client toward HTTP server. Okay. So what's really going on here is that in this particular folder we have a file called p4a.html. Okay. And what the server is doing is making that available to browsers which request for that file. Okay. So here what your browser is saying is that in this particular machine, there is a file called p4a.html at this location, and I would like you to give it to me. Okay, so that's what your browser is actually doing. In addition to that, your browser is actually doing one more thing. Once it actually gets the HTML file, it's actually rendering that on screen for you. Okay, so I will show you how an actual HTTP thing works based on our simple server. Okay, so 37 projects. Discussion. Okay, so let's look at this. So if you look at this is in 537-2/public. There's a folder called P4 which has all the files that you require for a very simple web server. Okay, so what we're going to do is we're going to first run this web server and then see how it actually works. So now we're going to say something like we're going to run this server and we're going to do it on port 5003, which is great because like I didn't compile. Okay, so now our server is running. So I can say stuff like the machine on which I'm running is called adg desktop 05.cs.wisc.edu, and then colon the port that we gave. Okay. I hope this works. Okay, it should not take this long. Let's try that again. Okay, well, we'll see what's going on. Okay, so let's go to the same folder. Can you guys see? No? Okay. So discussion today. Okay, CP4. So you actually provided a very basic client so that you can communicate with the HTTP server. Okay, so here I'm going to say this is the host name, our port is 5003, and let's say I want home.html. Okay, so what you see here is the response that you get from our HTTP server which is running. Okay, so it basically says the length of the content is 253. It actually was able to retrieve that file, so it says 200. It's okay, and then it has the actual web page content. Okay, when we do this request from a browser, what the browser is additionally doing is it's parsing all of the stuff and then displaying it on screen for you. Okay, which should have worked. I am not sure why. Maybe we need to be in the same network to access that. Is there a mistake somewhere? I could do one other thing. So what I'm going to do is I'm going to start up X and I'm going to launch a browser. And we're going to see if it works on the same host machine. Okay. All right. Firefox may give some weird errors. Let's try anyway. Okay. Yeah. Blah. What about Chrome? Come on, some browsers start, please. Since we're tunneling over X, it takes a really long time. Print report. Okay. Well, we got something. Wow, the rendering is horrific. Okay. Okay. Click. Yes. Okay, this is in slow motion. Now you guys can understand how it will be in 1980. All right. So let's see. Okay, I don't even know what I'm typing. Refresh. Okay, good. Seems to have become better. Okay, good. All this trouble for this. Okay, so it does not work on other hosts. I did not know that before. Anyway, so basically, if you open up a browser on the same machine and then you say on port 5003 is where you're running our stuff, then you're able to actually access the page. Okay. So this was actually served to you by the same server that we communicated with using the client. Okay, it's just that your browser is taking that information and then rendering it for you. So if you look at here, look at what it says, right? Test web page and is simply awesome and whatever. All of this is the same thing that was sent to your browser. Okay, just that the browser looks at this whatever is in the body of this HTML page and then renders that. Okay. So in your case, what you will have to do. Oh, and by the way, while you're running the server, you see all the requests that we are getting, right? We try to access home.html and apparently also favicon.icon. So if we try to access something else, let's say, this is a bad idea, but still. Okay, let's say we try to access this. Okay, then it gives us a 404 not found there. Okay. By the way, interesting historical fact. The reason if it cannot find something and it says 404 is because when the internet was first invented in CERN, these were all like physical rooms. So they actually had in CERN like a room for everything that was connected to the internet. And if you couldn't find a file, you went to room 404. So that's the reason why the error's code is 404. Okay. So your website is actually telling you that, right? So it says this was what I basically sent to this file. I said not found. I got the request for this and so on. So you can see that it is your thing that is serving it. Okay. So this is all pretty basic stuff, and the code that we're given you will allow you to run like a server and a client. Okay, but it's not particularly awesome code because if we gave you awesome code, it would take a long time to understand. So it's very simple and like hacky code that you can use to get something up and running. Okay, and it's relatively simple to understand. So let's shut down our server. Make clean. Okay, so what should I show you first? Let's look at server.c. Okay, it's a very simple web server as we can see in the comments. So you can see that there is a while loop, and in the while loop it's not doing much. It's accepting a connection. So when your client says I want a web page, it actually needs to establish the connection, as Mark pointed out, to the web server. Okay, and once we have connected to the web server, and in using that connection we can actually request for files and receive files and so on. So what this particular code is doing is it's saying I'm going to create a connection and then I'm going to wait for a connection to be formed. Once that's formed, I'm going to handle this particular request and then I'm going to close the connection. That's all that your web server is doing. Okay. Your task is to make this more awesome. Specifically to make it more awesome by adding threads to this. Okay. So basically, the way you will find out if it's like horrible or not is we have something called dynamic pages. Okay. It will take a really long time. Oh, we shut down our website. Right. So the page that you first saw is called a static website because every time you request it, you basically get the same output. You can also have dynamic pages wherein depending upon the parameters that you pass to it, it does different things. Okay. Here we have a simple CGI program which basically will do something before it displays that page. In our case, it just spins for 5 seconds. Okay. So you can imagine that if you give our web server 2 CGI requests, one after the other, the second request will have to wait for 5 seconds for the first request to finish. Okay. Ideally, we don't want to do that. We want 2 people to be running CGI requests to our web server at the same time, right? So what you will do is you introduce threads so that each thread will be handling one request. Okay. Now the very naive way to do this is to get a request, spin up a thread, and then like handle that, and then when it's done, kill the thread. And then when you get a next request, do another thread, and so on and so forth. But we want you guys to do slightly better than that. So what we want you to do is we want you to pre-create a set of threads. Okay, and we will tell you how many threads to create. Let's see. Blah, 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 blah. Right. So we will tell you how many threads to create. Okay. You have to create so many threads, which of course means that we will expect you to handle that many requests in parallel at the same time. Right. So you have to create that many threads, and then in order to synchronize between those threads, you'll need buffers, and we will tell you how many buffers to create also. Okay. So your task is really simple. So you have one master thread which basically accepts a connection from your client. and then it will say it will put the request into some buffer, meaning that some thread is responsible for handling them. Let's say you have 8 threads and you have 8 buffers, right? So one way in which this could work is the thread will look for something in its buffer, a file name, for example. If there's a file name, that thread will handle that request. Okay. So your main thread or your main program, all it will do is it will accept a connection and then put the name of the file that's being requested into some buffer. Okay. Now, of course, there are multiple threads here, and you need to synchronize between them. So, and we expect you to do this using condition variables. Okay, we have seen this in class. This is a classic producer-consumer problem. Your main thread is producing all these requests for all your worker threads. Your worker threads just need to check the buffer and then retrieve that request and work on it. Okay, so it's a very, very simple problem. Okay, let's see. So we have given some hints about the main structure of the program. It's very simple. Most of your work will be done in server.c and request.c, which is the meat of the program. Okay, so server.c is what we just saw. It's the program that is the main for the server. It will accept a new request, it will work on it, and then it will send the response back to the client. Okay. The request.c actually performs things like, is this a static file, is this a dynamic file, how do I run a dynamic program, and so on. Okay. The 537.c is just wrapper functions. You don't need to touch this at all. Okay, unless you're actually adding to it with your own wrapper functions. But basically, let's say you do an open, right? That open could fail. So in your program, if you are writing your own functions, you need error handling every time you do the system call. That's really annoying. So what this 537.c does is it wraps all of that for you. So it will automatically open a file, and if that did not work, it would automatically print an error message. So this is sort of like error handling done for you for many system calls. Client.c is what we just use to communicate with the server. Yeah, so this is client.c. Okay, it just sends a request to the server, and then like whatever response it gets, it just prints on screen. Okay, this is serial code, so it only does one thing at a time. So you want to make it so that it does multiple requests at the same time, right? One way of communicating with your web server is through this program. Another way of communicating with the web server is through your web browser, because it's also just a client for a web server, right? But things like spinning up 100 requests will be easier via this than via your browser. So that's why you have the client.c. Okay. Any questions so far? Okay. Let's see. What else do I want to tell you? So so that's the normal stuff that you'll need to do. So there is some extra credit. The extra credit is basically you have a number of requests that are pending, and you need to choose how to do a particular request. You can use file size as a proxy for jobbing, right? So if they're requesting, for example, index.html, you can then stat index.html, see how big it is, and then say this is going to take, this is 500 bytes, next request is 1000 bytes, so I'm going to do this request first. Okay, it's really, really simple extra credit. So everyone who does the main project should also attempt this. Okay, so it's basically going to take you like an hour to finish. It's very simple. So yeah, that's basically it for this project. If you have any questions, send email. One reason that we're making P4A easier than normal is because P4B is really hard. Okay, and the sort of expectation is that you will all finish this off very quickly and then move on to P4B, because P4B is harder than P3B. Okay, so that's the sort of setup that we have. So, oh, and the other thing, right? So when you're working on the project, right? Many people need to make this choice between, do I submit this today and not lose 10% of my grade because I don't have any late days, versus do I do this in full but have like you lose 10% of my grade, right? I'd always encourage you to do the whole project. Okay, if for some circumstances, like basically you had a midterm or whatever, and that's why you can't complete the whole project, you can always just send me email. Okay, we are not like too picky on when you submit your project. So if you have a valid reason, like you are traveling or you were sick or you had a midterm, right? We are totally happy to extend your deadline by a day. So whatever it is, don't make the choice of like not implementing stuff and submitting. Okay, always do it. Use a later if you have to. Come talk to us, and then we may be able to extend the deadline for you. Okay.
But using like they would be, we don't get penalized.
Yeah, I mean, like, I'm assuming if you have already used it.
Oh, okay. Okay.
Any more questions? Okay. Let's see. So that's basically it. So next week I'll be showing like a more detailed demo for P4B, which is more complicated. We won't be able to complete it if we start now. So do you guys have any questions? Okay. All right. Let's see. In that case, let's look at something else. So I thought I'll show you some stuff related to what we learned in class yesterday. So there are really interesting tools out there when you are working with like storage and with file systems. Okay, so this is one tool. So what this tool does is, remember when I told you that the file system runs on top of your block device, right? So your file system gets some requests, your block device gets other requests. Okay. So what this does is, if you run it on a particular block device, it can visualize what the requests look like for you. Okay. To give you an example, let's see. Okay, so this is one way of like visualizing it. So this is your disk offset, your block device, and this is like where in the disk we are doing writes and reads. And you can see it's clearly a very write heavy workload. Okay, so in this workload we're just like um, reading from like in big stripes all across the disk, right? The second graph shows you throughput. So you get up to speed and then you keep at like 400 megabytes per second, which means that they're using more than one disk or a very, very expensive disk. Okay? And as you can see, we can also look at the seeks that are done per second. Okay? The seeks, if you remember, the more seeks you do, the less performance you get. Okay? So if you have a workload that's like full of seeks, then you will not like really get good performance. So in this workload, we can see that there are only like 2 points at which it spikes. Apart from that, it's mostly, it doesn't seek at all. So we can see that it's a mostly sequential workload. Okay. And finally, remember that there's 2 ways to look at the output from, or the performance from a disk, right? One is how many megabytes per second are we seeing, right? So that's more relevant for sequential bandwidth. Like if a disk can do 100 megabytes per second, we expect to see something close to that. But if you're doing a lot of random requests, that's usually measured in terms of IOPS. How many random requests per second can we actually do? So IOPS is basically IO per second, right? And we can see that this array is like really good, right? So they can do around like 5,000 random requests per second. Okay, so so you don't actually need any permissions to run this tool. You can do it on your laptop or whichever machine you're running. So I'd highly encourage you, if you're interested, to sort of like download this and then set it up and then run it on your disk and then see what activity is going on. Okay. Let me show you some other interesting animations. Hopefully this will work, but maybe not. Okay, let's try something else. Oh, my internet is flaking. Okay, stop. Okay. Great. Okay. Let's try this one again. No. Okay. Where does it crash my whole thing? Let me see. Oh wait, no. All right. Let's try this one. Okay, none of them work. I do not know why. Because when I checked today morning, they were actually like going up. But anyway, the sequencer tool is from Oracle, so I sort of like highly encourage you to all check it out. So now that that demo failed, let's try something else. Let me see. Oh yeah, okay. So how many people know about S-Trace? Very good. Okay, all right. So S-Trace is basically system call trace. Okay, you are running some program and you're interested in seeing what system calls actually happen below your application level to the OS. Okay, so let me show you an example of that. So we all know what ls does, right? So it just lists everything in the directory. So now we're going to look at, well, before that, okay, so that ls doesn't have much of an output. How many people know what touch does? Yeah, it just creates a file, and if the file already exists, it updates its modified time. Okay, so here we have an empty file called b. Okay, so all right, so ls should just give us b. Okay, so simple output. So if we do strace ls, okay, I'll just run it for now, and then we will go through it more slowly. What it's showing you is all the system calls that are done by executing this simple program. Okay, and we can actually see everything that's going on. So there's a lot of stuff that goes in just for ls. Okay, let's go through this a little more slowly. Of course, that doesn't work. No, never mind. Okay. Well, okay, got it. So we can see that the very first call that goes through is execcv. Okay, so this should be familiar to you guys. We've already done this in our project. So execcv does that. Next, we have the system call brk. Do people know what brk does? I mean, you should have seen a variant of this in your xv6 project. Okay, no? It allocates memory. Okay, so when you do malloc, you need to grow your heap. Okay, and that is done using the brk system call. Okay, so it does exec cv, it calls brk so that it can extend its heap. It does mmap of some region. There's a lot of like, so you can see that all of these things are your libraries, right? It's loading the SC Linux library. It does a bunch of stuff for that. It's loading there at different locations, and then it's trying to load some other stuff, but it's getting an error. Okay, so a bunch of different locations, it tries to load its libraries. You can see that it also calls the stat system call. Okay, so stat is very useful if you want to find out if a particular file exists or not, but you don't want to do anything with it yet. Okay, so if you just stat this call, if it returns 0, it means that there is an actual file there. So it's basically it's using this to figure out if like there is a lib folder there. Okay, it does more mmap, it does more close, a lot of stuff in a very similar vein. Let's do something more interesting. Okay, so if you give a command like this to strace, what it does is it will only look for those system calls. Okay, So what you're seeing here is all the open system calls that was done as this program ran. Okay. So similarly, we can do write. Okay. And as you can see, the write system call is actually writing what we see as ls output. Right. When we do ls, we see 1 and b as the output, and that's actually being written to standard output by the program. Okay. So in this way, you can usually decompose the behavior of your entire program using just system calls, right? Because it really doesn't matter what else it does, because it has to use the system calls to communicate with your OS. Anything that it prints on screen, anything that it writes to a file, anything useful that's being done that someone external can see will need a system call. Okay? So even if you don't have the binary for a file, right? Ls we don't have the binary right now. We're not looking at the source. You can still use this program. So you can use this to figure out what a program is doing even when you don't have the binary. Okay, so it's a very useful tool. So if you do manage trace, you can see that there's a lot of like different options there. Okay, you can basically look for like different groups of like system calls. You can see you can trace the system calls of a parent process and a child process. It's very useful. So this is one tool that you should definitely be comfortable with by the time you finish cycle 7. Okay. Let me see. What else do I want to show you? There we go. Okay, so there was, I mean, I wanted to just show you all the things that are related to the file system. So -e trace equals test. Okay. Okay, so this is totally a much smaller version, or not that small apparently, but a much smaller version of like what's going on. So can you see this system call? So this is basically getting the D entry, okay, which basically means you're reading your directory. Every entry in your directory is called a D entry, okay. So we have a system call for looking for that stuff. Stat you already know, read you already know. Oh, by the way, why are we seeing this? What does this mean? Yes? Correct. So if we see this in a read, right, without knowing anything else, what you're seeing, you can tell for sure that it's reading a binary file. Okay, if it has a ELF binary, the header in it, it's reading a binary file. Okay. Let me see. I think that's pretty much all we had to do here. Let's do something else. Okay, so we have stat B, which basically shows you all of the information about that file B. Okay, and of particular attention is this. Okay, so it says it's a regular file. Okay, there are different kinds of files in your file system. So I didn't get to this part yesterday, but there's things called like hard links, symbolic links, files, and directories. Okay, so this is basically telling you, yes, this is a normal regular file. It's also telling you that it is empty. Okay, so stat gives you a lot of information. And remember that I told you about the inode number, which is the core of the file. So that's basically found here. Actually, let me show you a link for this. Okay. So we've seen stat. So now there's like 2 files in the system. Okay. Now if we do BL, we can see that it has the same inode number as B. Okay. I just created a link between B and BL, and they both point to the same core inode. Okay. Interestingly, it also shows you the number of links for that file, right? So previously it was just link 1. There was only one name which was pointing to 3935451, but now there's 2, B and BL. Okay. Now, when you remove BL, right, what you're actually doing is just you're decrementing one link to the same inode. Okay, so basically you can delete whatever name that you have for this link, and as long as there is at least like one name available for this file, the file will be kept. It will not be deleted. You're just deleting the name of that particular inode. But if it's the last link to this, then you're actually deleting the inode itself. Okay? Yes. So, right. So basically, the information, everything that's in stat here is all for the inode. Okay. So the inode is a regular MP file. There are different names for those things, but the inode itself is just a regular MP file. Okay. We can also have a different kind of link. So it's called a symbolic link. Okay. So, okay. So now if we stat BSL, then it tells you it's a symbolic link. Okay, and I'll show you what the difference is between a symbolic link and a normal link. So let's do BBL. So now we have three files. We have B, we have BL, and we have BSL. BSL is the symbolic link to B. Okay. Now the interesting thing here is that, let's say I remove B. Okay. So I'm removing B. I will still be able to do operations on BL. Okay. Because as far as BL is concerned, it's pointing to the same inode. It doesn't really care that there's no name called B. Okay. But if I try to do this, then it tells me there's no such file or directory. And the reason for this is that, let's do, okay. So this basically shows you the symbolic link information. So BSL, the symbolic link, is pointing to B. It's not pointing to an inode number. It's pointing to an actual path. Okay. And if we remove that path, the symbolic link is hanging. It's like a hanging reference to that file. So if it can't resolve this file, then this will not be able to work. Okay. Now the reason that we have these symbolic links, which seem like less awesome than hard links, is because when you do BL, right, what does it actually do? It creates an entry that points to the same inode number. Okay. And this inode number is unique in a file system. Okay. So if I show you, I can show you the list of file systems that are currently there. Okay. So these are all the different file systems that are running on my machine right now. Let me see which ones. So look at this, for example. We have the Scratch folder, and then it's running on this block device dev/sda6, and it's of type ext4. Okay, so I can only create hard links between two files in Scratch, or two path names in Scratch, because the hard link will be related to some number like x, and that x only makes sense to Scratch. Okay. So if you look at temp, that's also running ext4. So there will be a different file with the same inode number. It's unique to each file. Okay. So this is why you need symbolic links. So in Scratch, I can create a symbolic link to some file in temp, because I just give you a path. I can say create a symbolic link to /temp/a, and that would work. Okay. So that's why we have both hard links and symbolic links. Yeah. I'm not sure I completely understand your question. Let's do what we say. Okay. So we are, let's say we create B. Okay. Yes. Yes. So there is no difference in any way between BL and B. They both point to the same file. Okay. So let me show you. Echo hello to B. Okay, sorry. All right. Okay. So now if I cat BL, this. Oh yeah, I'm sorry. They have different inode numbers now. Okay. So if you stat B and you stat BL, they actually have different inode numbers. That's why it doesn't work. It doesn't matter if it's the same name. No, it doesn't. There's only one inode. Okay, so let me see. Okay, so if we cat B, it says hello. Now I'm going to echo world to BL2. Okay, now if I cat B, it says hello world. So you can write to either of those files, it's going to be the same thing. It's only the underlying inode that's getting changed. You still look confused. So how do I make this clearer? Okay, so let's see. Where are we? Oh, here we go. I was wondering if I could show you the resolution to inode number, but it's not visible at this level. It's inside the file system. But if it helps, think of it that way. Okay. Whenever you're trying to read a file, you will resolve your path name into the inode number. Okay, and then you do all your operations on just the inode number. If two files are there and they have the same inode number, it's going to be the same. It will point back to the same file. Okay, so B and BL, they are both point to the same inode number. So operations on one will be reflected in the other. Okay, yeah. Right. The point of having hard links is that you could basically have your files distributed all over the disk. Okay, but let's say you want to do some processing at a central location. You can just create hard links to all of those files, do your processing, and then delete your hard links. Okay, instead of like traversing through the whole file system, you have one location at which you can find it. So it's just like a different way to access the same file. Okay, yeah, great. That's a good question. Let's try. I don't know off the top of my head. So let's say I do chmod 000. I don't even know if it's possible, but we will try. To BL, that works. So it says permission denied, but you can cat B. So yes, the answer to your question is yes. Yes. Oh, sorry. What is pointing to it? BL2? Okay. Okay, so you still can. By the way, like the reason that you can is because your D entry has metadata associated with it, or your directory entry. Okay. I'll make this more clearer in class. Okay. You have some information stored in your inode, you have some information stored in your directory entry.
Okay. So when you do the change of permission before you do the permission should be the same.
Let's try it out. So we have touch C. Okay. So chmod 000 C. If I do this now, I can't even link it, I believe. We'll see. So it's permission denied. But you can link it. Okay. Permission denied. Yeah. Cool. Yes. They are names and associated metadata for files. Your names are stored in your directories. That's different from inodes. So you could have an inode with no name to it, just that nobody will be able to access that. Okay. You could also have a name. Well, I don't think it's strictly possible to have a name with no inode associated with it. But you could, I mean, for example, for a symbolic link, you could definitely have the case that it is pointing to some name and that name no longer exists. Okay. Any other questions? If not, we're done for today. Thank you.